All right, guys. We are going to leave the fourth dimension here. I have something set up so that hopefully you're going to be able to see me as I'm talking and see what I'm doing on the whiteboard at the same time. It's the first time we're trying this, so we'll see if it works. If it works well, hopefully these are the videos we'll do in the future. So I'm going to bring up my interactive whiteboard now, and we're going to talk a little bit about covalent bonding. So let's move that out of the way. Covalent bonding. Covalent bonding is different from ionic bonding because instead of transferring electrons from one element to another element, elements share electrons. It's also different in the fact that covalent bonding involves only nonmetals. So we might look at something that's a classic covalent molecule, methane. Methane has the formula of CH4. So when we're talking about this, I have my central carbon atom with its 4 valence electrons, and it bonds and shares electrons with hydrogen. Hydrogen comes in and shares its 1 valence electron. So that everybody is happy. You end up with hydrogen with 2 valence electrons and carbon with 8 valence electrons, and you get a happy octet. So covalent bonding is the other type of bonding that we see here, and it has special rules to go along with naming as well. So let's get rid of this. Oh, we'll go orange. So naming covalent compounds. Unlike ionic compounds where you just took the name of the element and the name of the ion and put them together, covalent compounds have a little bit more information that we need to give them. First, we need to say how many of each element there are. So when we're talking about that, we use Greek prefixes to describe that. So we can have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You can have up to 10, and each letter has its own name. So 1, or prefix for 1, is mono. And we have di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. These are our Greek prefixes. And they tell us how many we have. So with all of these, we're going to use that plus the name of the elements to name them. So let me bring up my eraser. So we've said how many there are. Our next Wow, that didn't work very well. Let's try again. We name the first element with its Greek prefix. And then we're going to name the second element, but change the ending to IDE. And add the Greek prefix. So, to name a covalent compound, it's pretty easy. We have to figure out how many of each element we have. We name the first element with the Greek prefix, and then we name the second element, change its ending name from whatever it is so that it ends in "ide." So like for phosphorus, instead of saying phosphorus, we'd say phosphide. And we add the Greek prefix. So let's do a couple of examples. So our first example for this one CO2. We have 1 carbon, 2 oxygens. So if I were going to name this compound, it would be monocarbon, because there's 1 carbon. We have 2 oxygens, so it becomes dioxide. Now, in general, for the first element in any covalent compound, if there's only 1 of them, you only have to say the name of the element. You don't have to put the prefix in. So instead of monocarbon dioxide, most people just know this as carbon dioxide. Okay. Here's example number 2. And that's going to be P2O5. So we have P, which is phosphorus, and O is oxygen. So we know we have phosphorus. We have 2 of them, so we're going to put the prefix di in front of it. So this becomes diphosphorus. And then we have oxygen. Oxygen, when it's at the end, is no longer oxygen, it becomes oxide. So instead of saying we have 5 oxygens, we're going to say we have 5 oxides, and the Greek letter, or the Greek prefix for 5 is penta. So we have pentoxide. We drop the A when it starts with a vowel. So P2O5 becomes diphosphorus pentoxide. One more example. And for whatever reason, I decided to write out an example. CCl4. So we have carbon. That's our first element. We have 1 of it. Normally, when we have only 1 of them, we would put the prefix mono, but because it's the first element, we can ignore mono this time. So we're going to just say carbon. And now we look at the next element. The next element is chlorine. Chlorine, when it's ending, it becomes chloride. Instead of saying chlorine, we say chloride. And we have 4 of them. The Greek prefix for 4 is tetra. So we have carbon tetrachloride. And for those of you playing at home, carbon tetrachloride has a common name known as chloroform. One last example. Just because you can use this one to amaze your parents at home tonight. H2O. 2 H's, so it's dihydrogen. And then 1 O, so it becomes monoxide. So tonight you can ask your parents for a big glass of dihydrogen monoxide and see if they're amazed when you do that. So that's it. That's all you have to do for naming covalent compounds. It's very, very simple. Coming up with formulas is also very simple. Naming, you just tell me how many and what element. Now let's look at coming up with formulas. So if we're going to come up with a formula for a covalent compound, the name tells us what it is already. Disulfur pentoxide. We want to know what the formula is for that. Disulfur, 2 sulfur. Pentoxide, 5 oxygen. So it's S2O5. CBr4. C is carbon. There's only one of them, so we can just say carbon. Br, bromine. 4 of them. So we know we're going to have tetra. Bro, and instead of mine, it's mine. Remember, we changed the ending on the last element to IDE. So CBr4, carbon tetrabromide. It really is as simple as that. Writing formulas this time much easier than when we were dealing with the ionic compounds and we had to make sure the charges canceled out, use that crossing over rule, making sure that we had the simplest whole number ratio of the elements in the compound. Covalent compounds, much simpler because it tells you exactly what the formula should be. All right, we got one last thing to cover, and that is going to be naming acids. So, acids, we've all heard of them before. We want to make sure that we know what they are. For our definition, an acid is going to be anything that can give up H+. So, something like this. There's my H that it can donate. So this is going to be an acid. When you're naming an acid, you have to look at what the anion is that it's attached, that the hydrogen's attached to. In this case, we have CO3, which is carbonate. When it ends in ATE, we actually will drop ATE and change to it to IC. So when you end in ATE, you change it to IC. So it's no longer carbonate, it becomes carbonic. Acid. So when we're doing this, we have to look at the ending of our anion. If it ends in ATE, you drop it and change it to ic, and the name becomes carbonic acid. We ignore this hydrogen. We don't care about that in the name. We just want to name what polyatomic ion we're dealing with. That works with anything that is in ATE. So let's do an example. Let's do an example. So let's say we have this compound. We know we have our acid donor right here, this H. We got to look at our anion. SO4 is sulfate. It ends in ATE, so we're going to drop the ATE and change it to IC. So it becomes sulfuric. And then we add the word acid. It changed a little bit. Sulfate became sulfuric acid. There's supposed to be a 2 there too. H3. Let's try this one. Okay, we have H3 right here in our compound, but this PO4 is what I'm looking at. That's my anion. PO4 is phosphate. Ends at ATE, so we're going to drop the ATE and change it to IC, so this becomes phosphuric. And then we add acid. So that's one example. Let's look at a different example on that. HF. Okay, we have this H plus in front right here. We still know, so we know it's still an acid. It can donate that proton. It can donate that H plus. But now, instead of something that ends in ATE, instead of one of those polyatomic ions, we have an element here. This is fluoride. When you end in IDE, we still change it to ic. But there's a second step involved. We're going to add hydro in front of it. So we know this ends in IDE. We change it to ic and add hydro in front of it. HF, as an acid, we name it as, would help if I wasn't standing in my own shadow. Also help if I could spell. So this becomes hydrofluoric acid. Ended in IDE. We change it to ic and add hydro in front of it. We call this hydrofluoric acid. Let's try another. This is HCl. Please note that that is a lowercase l, not an uppercase I. People get this confused all the time and want to write HCI. Where's my HCI? How come I can't find HCI? Where's CI on the periodic table? There is no CI on the periodic table. It's Cl. If it was an I would write it like this, or lowercase would have a dot. It's HCl, not HCI. In case you couldn't tell, big pet peeve of mine. So let's get rid of that. HCl, all right? We've got our H, so we know it's going to donate a proton. We're going to focus on this Cl. Cl is the chloride ion. Our thing is ending in IDE, so we're going to change it to IC and add hydro in front of it. So this is hydrochloric acid. All right. One last example of this type. This time it is an I. See, I crossed the two things up there. This is a capital I. Once again, we have our H in front, so we're going to focus on our anion. Our anion here is iodide. Ends in IDE. So we're going to change it to ic and add hydro in front of it. So HI becomes hydroiodic acid. All right, we have one last type of acid naming to go over. So this one last type is when it ends in ITE. So my example is going to be H2SO3. We've got our hydrogen, so we're going to focus on our anion here. This is sulfite. See, it ends in ITE. So we have a new rule. We're going to change ITE to OUS. So the name of this one becomes sulfurous acid instead of sulfuric acid. Sulfuric acid is H2SO4. Sulfurous acid is H2SO3. And there's a big difference between the two of them. They don't react the same way, which is why it's important that we name them correctly when we're talking about it. So let's do another example. H2PO3. PO3 is the thing I'm going to focus on. I see my H in front, so I know I'm dealing with an acid. PO3, that's phosphite. Ends in ITE, so we're going to change it to ic, not ic, we're going to change it to us. So this is phosphorus acid. Not to be confused with HP. Actually, it would be H3P, because H3P is going to be hydro. hydrophosphoric acid. But phosphorus acid is H2PO3. Names mean a lot. Acids are tricky, I understand that, which is why you have all that practice to do. Make sure if you're having issues with this that you ask questions. I have office hours this week virtually. You can just click on the date in the Astro Bulletin. That will tell you when I'm available. Or if you're in person on that day, you can always drop by 322 and ask me your questions then. All right, we'll see you in class this week. Hopefully this helped.